So thanks for joining us this afternoon for our last of 6 webinars on the topic of climate resilient buildings, presenting research that's been done at the University at Buffalo. My name is Nick Rakovich. I will be leading you through today's webinar. Before we get started in the meat of the presentation, I do want to thank NYSERDA and especially Amanda Stevens, who is the project manager at NYSERDA, for supporting this work over the last now close to 4 years. This webinar also really was supported by the U.S. Green Building Council New York Upstate chapter, and especially Tracy Hall. Also want to thank a number of graduate students who have helped with putting this research together. So Lizzie Gilman, TJ Mulligan, and Hope Forgas, who is here today, making sure that this presentation goes smoothly. Though if anything goes wrong, don't blame her. It's probably me messing something up. The research that we're talking about, again, is something that NYSERDA has supported for the last several years. All of the research that we have done as part of that project is being posted to this website, ap.buffalo.edu/adaptingbuildings. On that site, you can see a number of different reports that we've prepared and we've actually talked about as part of the last couple of webinars. You can also find, though, hopefully by next week, we will have all of the webinars, video recordings of these posted to there, as well as PDF copies of the PowerPoint presentations for you to use them for your own purposes. When they are posted to the website, they're not going to be something that qualify any longer for AIA credits, but it's there really for your own learning purposes. So before we dive into the information, again, just want to remind everybody that you are on mute. If you do have questions as we're going forward, please just use the chat feature. And with that, we can see that if there's something that just can't wait. But otherwise, we'll wait till about 12:50 to go through and unmute people and have them have the opportunity to ask questions. So today we're going to be talking a lot about how changes in temperature especially impact buildings. And part of the reason why we're interested in that is according to reports like ClimAid, which is the New York State Climate Adaptation and Mitigation Study, the main one produced by NYSERDA, the number of days over 90 degrees Fahrenheit is projected to increase in the future for every region of the state. If you joined us for the Climate Hazards Workshop, which was the second workshop that we did a couple of weeks ago, you'll know that by the 2080s, the days over 90 really are expected in many cases to expand threefold or more. In addition to having those higher heat days that are of great concern, we also are starting to see some evidence that the number of cold snaps may increase as the Arctic warms, though this is an area of great debate right now and requiring further research. But as we look to the future and we think about the climate of New York State, right, we're in all cases, as it relates to precipitation and many other types of things, looking at more extremes associated with climate change. And really this, temperatures go right along with this. One of the things we're very concerned about going forward is that the frequency and duration of heat waves, which are defined as 3 or more consecutive days with maximum temperatures at or above 90 Fahrenheit, are also expected to increase. And when we do have these high heat days in New York State, that's where we begin to see the really significant heat-related illness and death. In New York, most of the heat-related illnesses and deaths occur indoors, so buildings are actually acting as a moderator of that outdoor climate. They can either exacerbate those extreme conditions, you can have spaces that are hotter than the outside environment, or with good design and thinking about how the building responds to the climate in general, you can have buildings that actually begin to moderate some of those temperatures. This is something that's very significant in terms of its impact on deaths in the state. So by 2050, one study estimates that the total heat-related deaths in New York City alone are projected to increase by between 204 and 206 deaths, 68 deaths per year. If you look at that in terms of an annual economic impact, It's right in line with some of the worst types of climate-related hazards that we have in the state, that it could be between $1.5 and close to $2 billion, again, just in New York City alone. And this really has to do with the fact that heat waves do kill more people every year than any other type of natural disaster. And in fact, if you take heat waves and you compare them to all of the other natural disasters combined, they still come out on top as having the most number of illnesses and deaths associated with them. As we start to look at some of this data, I want to point folks to some really important resources and things that may be helpful as you're starting to think about these on your own design projects or projects that you're thinking about building. One of the great resources that we tapped into for doing this research was the New York Climate Change Science Clearinghouse. Not exactly something that easily rolls off the tongue, but if you remember NYCCSC, there's a lot of great information on this site that can be very helpful for planning out and looking to see how the different environmental variables are expected to change in many of the different locations of the state. As you go into that website under the data portal, one of the neat things that you can do is select a different geography. So on the map on the left, in this case, it's selecting the entirety of the state, but you can actually also drill down to each of the counties in New York State or actually look at some of the specific weather stations. One of the neat things that this site has, though, is actually some of the key kind of building environmental metrics that we might use and begin to think about in terms of sizing systems for a building. So in this case, one of the things that's listed is the cooling degree days over time. You can see in this chart, which is the cooling degree days for New York State as a total, they've been relatively stable over time. But as the climate begins to warm, as we move out of where we are right now in 2019 out to 2099, you can see that there's expected to be kind of a significant increase in the number of cooling degree days, and actually that curve is beginning to increase in steepness as the climate begins to warm up. You can use this information certainly as you begin to plan systems out. On the site, you can also go through and begin to click through and look at different climate change projections or different times of the year to get the key data. What it does, and it's very helpful in that way in terms of, again, thinking about how you might design for things. But one of the things it doesn't actually have, and there's been some talk about having these things in the future, is the data that you actually need for building energy modeling, which oftentimes is called TMY data for typical meteorological year. So the research that we're going to present to you today is actually based on work out of the United Kingdom. It's based on the Chartered Institution of Building Services Engineer, or CIBSE, report called Climate Change in the Indoor Environment, Impacts and Adaptation. For this research, we also use the NYSERDA New Construction Program simulation guidelines. And so if you've worked with NYSERDA before to get energy efficiency incentives for projects, you'll know that there are very specific guidelines on how you begin to model those systems to look and see for instance, how much energy savings, how much energy demand savings there are, but also things like greenhouse gas emission reductions, et cetera. We ran the models in eQuest version 3.62 using files originally created by LNS Energy Services for the technical assistance studies in support of the NYSERDA New Construction Program. So LNS Energy Services, which is a great engineering firm out of Albany, out of Clifton Park, actually took a number of projects that they had worked on as part of the NYSERDA New Construction Program and reran them and looked at them under a couple of different climate scenarios. The models that we ran used TMY data initially, so we looked at two different types of TMY, the first being for the last 30 years, so from 1986 to 2015, just to get a baseline to understand, if you were designing this under a typical approach, what would some of the energy use be in those situations. We also looked at the TMY for the last 6 years with the idea that there may have been more warming or more extremes in those cases, and we wanted to see what some of the variations in energy use and temperature would be under that. We also had, and we worked with a partner called Weather Analytics, which is a weather data firm out of Maryland. They also developed some files for us that they called Extreme Meteorological Year, or XMY data. So the two files that they created for that are XMY maximum files. So for the last 15 years, looking to see all of the years and basically all of the temperatures that were the highest in any of those given situations to try to understand how buildings might perform under heat waves or thermal extremes in that direction. And then also XMY minimum temperatures to really look at the coldest that we've had. And in some cases, in places like Buffalo, for instance, the winter of 2015 was actually January and February were some of the coldest ever recorded in Buffalo's history, associated with things like the polar vortex, which I mentioned earlier, potentially is something that could increase in the future. So we looked at 5 different case studies across 7 different climate zones. So the 5 case studies that we have listed here are low-rise residential buildings, multifamily residential buildings, commercial buildings, industrial, and also educational structures. And we looked at those against the 7 different climate zones in the CliMate study. So NYSERDA actually breaks up the state into 7 different distinct bioregions based on the climates that are there. Some of the climate zones, for instance, include the Great Lakes Plain, which is Region 1, where places like Buffalo and Rochester are. New York City is in Climate Region 4, which includes the 5 boroughs and then also Long Island. And then as you get up into the North Country, into Region 7, which is really the Adirondacks and the area around Plattsburgh, those are some of the very distinctly different regions or bioregions that we have within the state. We selected, though, these 5 different building types really for a couple of different reasons. One of the big reasons, though, was we were looking at what comprises the majority of the building stock. So when you look at low-rise residential buildings, they're actually about 75% of the total statewide floor area of all of the buildings. When you look at something like the multifamily residential buildings, while it's only something that's 13.4% of the total statewide floor area, it's actually something that is about 40% of the building stock in places like New York City and Long Island. We also then looked at commercial buildings because we were interested in seeing how these would perform, but also because their recovery potentially after an extreme event is something that is really critical to the state rebounding and getting in its economy going again. Same thing goes for industrial buildings. And last building type that we looked at was actually educational buildings. Although it's a very, very small percentage, 0.001% of the total statewide floor area, those types of buildings, things like high schools or middle schools, oftentimes are used in communities as a place for people to shelter in place. So we wanted to make sure that we started to look at their energy performance and also to understand how they might begin to perform in terms of things like heat waves or cold snaps. So in total, with the 5 different case studies in the 7 different climate zones, L&S Energy Services ended up creating 35 separate energy models and going through and then running those under each of the 4 different data that we talked about a second ago. So we actually had, thousands and thousands of different files to sort through. That being said, that's not really something we can go through and talk about every single one of those things during today's presentation. We'll be releasing this report on the website I mentioned earlier, hopefully in a couple weeks. What we are going to report out today is some of the statewide impacts. One of the key things we also took a look at as we began to run those models was to try to understand how these spaces, how different systems in the building, how long they typically last. And the reason behind this is we wanted to think about getting the different types of systems that are going to last the longest correct. So if you think about things like the orientation of the building, the foundation design, things like the wall and floor and the envelope of the building, these are all things that you really expect to last 50 plus years over the course of the life of the building. As you get into some of the other systems like ductwork and piping and getting down into mechanical and electrical equipment, this is something that just through natural replacement cycles, we're potentially going to see 2 or 3 or 4 cycles of replacement between now and 2080. So if we start to understand how the building orientation, the foundation, et cetera, performs under different climatic conditions. Getting that right, that's going to last with the building way out in the future when we see those extreme changes. And we still potentially have some time on the mechanical and electrical equipment. So there definitely was a lean towards, looking at things like the envelope, for example. We also were really interested in exploring an idea called passive survivability. And this is something that has beginning to be talked about quite a bit these days, and it's actually being incorporated into some different standards. Most notably, recently, the U.S. Green Building Council released something called RELY, which is a resilience standard, and they begin to have guidance in those documents about achieving passive survivability. LEED also has some pilot credits that include passive survivability. And while the specific details about how passive survivability works are still being discussed, and how the modeling of that works is still being discussed, the general definition that was developed by Alex Wilson is the ability of a building to maintain critical life support conditions for its occupants if such services such as power, heating, fuel, or water are lost for an extended period. Alex developed this idea really after Hurricane Katrina in 2005, when he saw some of the situations going on in the Louisiana Superdome, and also some of the conditions where people were sheltering in place after the hurricane without power, oftentimes in extremely hot conditions. And he's been working, now for close to the last 15 years on this idea, and it really is beginning to pick up steam. So one of the things we wanted to look at is to say, as we begin to change the building envelope in these different case studies, what does that mean for the temperatures inside the building? So I'm just going to move here now to begin to talk through some of the different case studies. The 5 different case studies, again, were the 2 residential buildings, commercial, industrial, and educational buildings. I'm going to start by going through and talking about the residential building, the low-rise residential building first. So there are approximately 4.75 million residential buildings in New York State. They represent about 90% of the total buildings in the state and about 3/4 of the total value of the building stock. And if you think about it personally, for many people, their residence is the single biggest investment that they will make over their life. Certainly also, though, residential buildings are important because it is the primary place where people eat, sleep, and live. And so if people are sheltering in place for something like high heat days, it's likely to be in some of these locations. There's also a concern as it relates to issues like passive survivability and energy use, because these tend to be externally load-dominated buildings, meaning that they don't have lots of internal heat gains from lights and equipment. And so what is happening outside in terms of changes in temperature and changes in humidity have a tendency to really change the temperatures inside quite quickly. So these types of buildings, as lighter weight buildings, oftentimes really respond quickly to those shifts. The model that LNS Energy Services analyzed was based on a 12,000 square foot, 12-unit apartment complex that was built in Brooklyn in 2008. This is an actual project, so these were the actual energy models that were analyzed as part of this process. You can see a screenshot from the energy modeling in the top right corner of the slide to get a sense of its massing and also just generally how it looked. The building itself was a 4-story light gauge steel frame structure with a brick veneer finish and a flat roof, and the building also had a slab on grade foundation. So this was intended and designed to be a lower cost building. It is intended to be affordable housing in Brooklyn, and so in responding to a little bit more temperate of a climate zone down in the city, it had sort of lighter initial insulation levels and also that slab on grade foundation. As we go through and talk a little bit about how we structured the modeling, I just want to spend a little bit of time in this first case study to explain how we went through this. So energy conservations, or ECMs, really were in all cases in all 5 of the different building types. We went through and tried to identify different things that could be improved. We also actually focused on the different types of systems that had actually been improved in these buildings as part of the NYSERDA New Construction Program. So in all cases, we had baseline systems descriptions. These were really what was in effect in the energy code at that time. So although in this case, for instance, there may be higher insulation requirements in New York State for some of these baseline systems now, we were looking at this, what it was designed as. In this case, in 2008, it would have been the New York State Energy Conservation Code of 1999. We also looked, and I had mentioned this before, about the effective useful life of some of these different things. So we tended to focus on things and to start first with the systems that would last the longest. So things like improved insulation, upgraded windows, and things like the roof are all something that are expected to last 20 years or more. And those three things are also something as an externally load-dominated building that potentially really drive heat gain and loss in the structure. In all cases, then, we took a look at how we could upgrade those systems and trying to estimate what the cost of those upgrades actually would be. So in the case of, again, this low-rise residential building, going from an R20 continuous insulation in the roof to R30, going from glazing with a solar heat gain coefficient of 0.5 to something with a solar heat gain coefficient of 0.28, U value of 0.6 to U value of 0.3. Also looking at things like high albedo roofs, which certainly help with heat gain, but can also help to mitigate the urban heat island effect. So having something that going from a dark roof to something that has a light roof. Other things that we looked at that also help with energy efficiency, certainly, but also potentially can help with heat gain in the structures was looking at things like interior lighting and AC equipment. Now, these strategies are not something that were universal to all of the 5 different building types. You'll see as we go through the different case examples that those begin to change, but I just wanted to give you a sense of how overall we structured the energy modeling. So taking a look at the statewide energy use, energy demand, cost, and emissions impacts, I think it's nobody would be surprised to see that when you begin to upgrade the envelope and when you begin to upgrade the building systems like the interior lighting and AC, you can see some pretty significant changes in terms of the annual electric usage. So in this case, dropped by about 28%, but also drops in the summertime peak and the wintertime peak. With the improvements to the envelope, there was also a small savings in natural gas usage and a decent reduction in the annual energy costs. One of the things, though, that we also wanted to try to calculate, because they are associated with climate change, is what are the impacts on emissions? So sulfur dioxide and nitrous oxide emissions, which are certainly hazardous in terms of human health, can cause things like ground level ozone, and also carbon dioxide emissions. And the reason we wanted to look at those is to make sure that as we went through each of these strategies for the different building types, that we saw energy savings, we saw greenhouse gas emissions. Because when we talk about adaptation, we're not just interested in protecting the building from what's to come in the future. We also need to begin to think about how we really reduce those greenhouse gas emissions. And so finding things that reduce greenhouse gas emissions and protect the people inside is really the sweet spot in terms of design. When we started to look at the climate resilience statistics, so you'll see on this slide a couple of different statistics that we generated from the models. The first thing was taking a look at the hours of loads not met. And the interesting thing about this was taking the buildings with the systems, with the building mechanical systems sized as they were actually designed, to see under several different weather conditions, under the TMY data, and also under these max conditions, did something like putting in the energy efficiency measures help reduce the number of hours that the building's systems could not meet the total loads. And in all the cases, in the case of this low-rise residential building, we see that it does significantly reduce the total number of hours where loads are not met by the building. Other things from the passive survivability, and again, talking about that as the habitability of the structure, even in the absence of power. So when LNS ran these models, they basically ran the building as though there was no electricity on. So They shut off the lighting, they shut off the mechanical systems, and let the system free run to understand what the maximum interior temperatures might be, but also the hours above 82.4 Fahrenheit. The first thing I want to walk through is just the maximum interior temperature. So you can see in all cases, by installing those energy conservation measures, it really is dropping the interior, that maximum interior temperature, by close to 10 degrees for all 4 different kind of weather conditions that we modeled. And that really is significant in terms of human exposure in a space. You can imagine, certainly as you get above 90 degrees and close to 100 degrees, the human body really begins to break down pretty quickly and can't shed that heat. But keeping things in the building under 90 degrees certainly can have a huge impact on whether somebody can ride out a heat wave event. The hours above 82.4, while that may seem to be a relatively random statistic, 82.4 corresponds to 28 degrees Celsius. And as I mentioned before, we used the CIBSE report as actually the basis for our study, and so we kept the same statistic. And so with this, we were trying to understand how many hours over the course of the year it might be above that threshold, which is really at the outer edges of the comfort zone. It's really starting to indicate heat stress for people. So I want to make a transition now to the second building type, talking about multifamily residential buildings. So again, in this case, this is a taller, more than the kind of low-rise residential buildings that you see all around New York State. There are approximately 750,000 of these buildings in New York State, so it is a significant part of our total building stock, and it does represent about 13.4% of the total number of buildings in the state. And again, as you go downstate, as you get into the 5 boroughs in Long Island, these are the building types that predominate. 40% of the building stock in those locations, are these multifamily residential buildings. And certainly we saw after things like Hurricane Sandy, a lot of people rely on these and are sheltering in these buildings even if the power is out. Like the low-rise residential buildings, these are also externally load-dominated buildings, though as they get into bigger or more sprawling buildings like the one that we examined here, they begin to move away from that. And as you have larger zones, and what we'll see in the data, these buildings tend to ride out a little bit better than the smaller residential buildings. The one that we looked at for our analysis was a 152,000 square foot building in Glenville, New York. Was based on an inpatient nursing facility, so certainly one of the facilities where people are at their most vulnerable. This building had a steel frame and concrete plank structural system, and it does have both residential, sleeping, dining, and common areas and offices. So as we looked at this building in total, there were more uses than you might find in just a low-rise residential building. We only looked at 2 energy conservation measures as part of this analysis. So moving from what was code at the time, a baseline code for both the envelope and the glazing, to a slightly upgraded system. So moving from R20 continuous insulation to R40, and from R13 to R26.9, and then improving the solar heat gain coefficient and U value of the glass. As we looked at the total impacts in this case on energy use, demand, cost, and again, emissions impacts, for this larger building, the better envelope had less of an impact on electricity usage. So we only see about a 3% decrease in both the summer and winter peak. There is some savings in terms of the natural gas usage, so about a 9.3% reduction in that annual natural gas usage. And again, a lot of that really would just be wintertime heat loss being slowed by a better envelope. A small reduction in the total cost. A lot of that has to do with there are a lot of other pieces of equipment in this building, so it's not saving as much as one might expect. And then very small emissions reductions. But again, things like the SOx and NOx emissions are important for human health, and certainly we're looking for, wherever possible, to reduce carbon dioxide emissions. Forgot to go through each of those 4 clicks. Sorry about that. As we looked at the statewide climate resilience impacts, so we really didn't see much in a shift of the hours loads not met. A lot of that we think has to do with that this was really a building that had a lot of large zones, so there weren't many hours where the systems actually weren't able to keep up with the loads in those cases. Might have also indicated that there were slightly oversized systems. And as we looked at the maximum interior temperatures, we did see small reductions in terms of the total drop in maximum interior temperature. So, which is important. Even the smallest amount of change is important for the type of facility that this is, which is a skilled nursing facility. But again, it's not as significant as something like the low-rise residential building, which is much more externally load dominated. The total number of hours over 82.4. So in this case, we saw significant decreases in the total number of hours that were over that threshold temperature. So in this case, you can see for the both TMYs, an average of about a 40% reduction in that. And certainly for the high temperature year, the max MY or the minimum XY, those are also brought down. So all positive attributes associated with those energy conservation measures. Diving into the next case study, taking a look at the commercial building. So again, commercial buildings are obviously important to the overall economy of New York State. We're interested in making sure that these buildings get up and running again, after we have some kind of event. They do represent about 6% of the total buildings in the state, but certainly they have an outsized role in terms of our overall economy. When we're trying to recover from climate hazards, in many cases, if you lose something like a grocery store or a gas station, that really can hamper efforts in other parts of the community. One of the key lessons learned from things like Hurricane Sandy was if food is unable to be served or, brought into locations, that really can slow down the entire process. To that end, we actually took a look, in this case, the model we looked at was a supermarket that was built in Madison, New York, about a 37,000 square foot building in 2009. It's a very simple building. It used tilt-up concrete construction for the building shell, and the roof was really just a metal framed roof with a metal deck covered with a standard kind of seam roof system. The different systems, the energy conservation measures that we looked at as part of this research, again, we're focusing a lot on the envelope, so improving to above code insulation in the walls and roof, bringing in daylighting controls. Daylighting controls as a passive strategy certainly can be important in terms of reducing the need for electric lighting, but that also can become important in terms of navigating through spaces and reducing total heat gain. If you can turn the lights off when it's sunny outside or when you have adequate light outside, that's certainly reducing some of the heat gain from that internal equipment. Also looked at above code glazing and better energy efficient systems and premium motors in this case. So there was obviously a lot of refrigeration equipment associated with this project. In terms of the energy savings, energy demand, and emissions impacts, so did see some pretty significant energy savings from those energy conservation measures. So for the electrical system, all around 20%, 17% for electric usage, and about 20% each for summertime and wintertime peak. I should mention that reduction in peak impact, peak usage is important also for keeping the grid operational. So certainly in terms of reducing the total demand on the grid, especially on these high heat days, can become critically important. Gas was also reduced, gas usage by about 10%. Total energy costs came down by 14.4%, and also saw significant reductions in both the SOx and NOx emissions and also carbon dioxide emissions. So again, all of these things, all of the energy conservation measures do and contribute to building performance. In this case, the energy efficient lighting design made the biggest difference in energy use. As we go through and take a look at climate resilience impacts, so really, again, with this type of system, there weren't many hours when the loads weren't met. In some cases, actually, you can see in the maximum extreme meteorological year file, adding more insulation to the envelope may have actually increased some of the cooling load in some of these cases because some of that heat is not able to escape from the building. Maximum interior temperatures are brought down slightly in the building, so only by about a degree in each case, which is small but still measurable. And the total number of hours that go above 82.4. And again, this is something that if the power was out, what are the days or number of hours that you're going to see over that 82.4 threshold? In all cases, they're brought down by about an average of 5% statewide. So again, small, but as we're moving to a building type that is more and more internally load dominated, we're starting to see those passive survivability impacts begin to decrease. And that really is something that we would expect to see in these data. Moving to the next building case study, which is industrial buildings. So there are approximately 90,000 buildings like this in New York State. They represent only about 1.75% of the total number of buildings in the state, but they are also a large part of the economy of New York State. And so understanding how these, again, might start to recover and also what might happen with these systems in terms of performance was something we wanted to look at. Certainly improving the energy performance of this building group is something critical to increasing the resilience of the building stock. So we went through and found among the buildings that had been modeled by LNS an example of a building. And it was really based on this small 36,000 square foot building in Ballston Spa, New York. And it was a relatively simple structure, not too unlike what we saw with the commercial building. So in this case, again, we focused on making some changes to the overall envelope. In this case, though, there was also improvements to the lighting design. So actually having or nearly having the total demand used by the electrical system, changing the different types of systems that were in the space, installing things like occupancy control, demand control, ventilation, etc. When we went through and took a look at what the energy savings were associated with this, not surprisingly, in a building type that actually has pretty high energy demands, you see some pretty significant electricity reductions. So on the order of a third. Again, about 30% reduction in annual natural gas usage, about a 40% cost savings, and really significant reductions in emissions. So again, on carbon dioxide, we really do want to still keep that in mind, even though we're also thinking about resilience as an issue. As we got into the results, though, of this building type, an interesting thing began to happen. So as we looked, for instance, at the hours of loads not met, one of the interesting things that happened as part of the analysis when we put the better envelope on the building, it actually tended to trap more of the heat from the equipment that was in the space, that was modeled to be in the space. And so the hours of loads that were not met actually increased in the as-designed building. And again, we think that just really has to do with more of that heat being retained in the space and potentially the air conditioning equipment not being able to keep up with it. The systems also, in this long, low-slung building, we also saw under passive survivability, so modeling this as though the power were out, that the hours above the maximum interior temperature actually went up in the as-designed building as opposed to the baseline. Again, we think it's because of the improvements to the envelope. And then also the hours above 82.4 degrees Fahrenheit went up for this building. So it brings up an important kind of cautionary tale that, as you're thinking about how you want to balance out greenhouse gas emissions and also resilience, you need to think about, how the building type is being used and how the overall form of the building is and how you want to begin to, balance both the reductions and the resilience or passive survivability impacts. We didn't think that the increases in the max interior temperature and also the hours above 82.4 were a crisis, primarily because you're probably not going to have people sheltering in place in an industrial building. And certainly industrial buildings are probably not going to be online without having power. But it is something to think about, and we'll talk a little bit more about that in the conclusions. Finding ways and protocols of beginning to do this analysis is probably one of the important next steps. So moving to the last building type, which is educational buildings. So there are approximately 14,000 educational buildings in New York State. Whereas the low-rise residential buildings are probably people's most important individual investments. Certainly the educational buildings are some of the city's biggest investments or municipalities' biggest investments. It's also where we tend to have some of our most vulnerable populations, which is our children. And so making sure that we get these things right is critical. While it is a small part of the total number of buildings in the state, it is something that it is a building type that often serves as an emergency shelter. And really thinking about how these systems perform, how they naturally ventilate, is really critical to not only increase the resiliency of the building stock, but also our communities as a whole. So the model that we took a look at in this case was a 192,000 square foot building. It was a single-story educational facility that was built in Auburn. It was actually originally built as a BOCES facility. In this case, we looked at, again, very similar energy conservation measures. So in the upgraded systems, we had additional insulation in the wall and the roof, higher efficiency lighting, things like occupancy sensors and energy recovery units. When we looked at what the impact of those energy conservation measures were, in all cases, they had positive impacts on electricity use and also electrical demand in both summer and winter. Natural gas savings were associated with those improvements. Total cost was certainly decreased, which is important certainly to the bottom line of a school district. And finally, we saw a reduction in the emissions associated with sulfur dioxides and nitrous oxides, but also carbon dioxide. So all positive all across the entire state. When we did these things, all saw savings. As we got into looking at some of the statewide climate resilience impacts, we did see with the improvements to the envelope and improvements to the systems that the total number of hours that loads were not met decreased. And so again, by putting in those more energy efficient systems, as we looked at some of the extreme temperatures in the different energy modeling files, we saw reductions in the total numbers of hours that those systems couldn't keep up with the loads. But like the low-rise residential building, if we want to have people begin to shelter in these spaces, we are concerned about the maximum interior temperature. And I think what was notable about looking at this is that the building is a baseline building, is a single-story school building, which is really common across upstate New York. You had a building that actually was approaching 105 degrees, which is not really safe for people to be inside. And so just some of those simple improvements to the envelope actually brought the temperature down 5 degrees. If you looked at additional things like really making sure that the space was cross-ventilated, I would fully expect that you could bring this down even further. But this is something that really does become important for the design of these structures, and something that I think and hope going forward we begin to pay more attention to. The hours above 82.4 Fahrenheit, again, that 28 degrees Celsius threshold, were also reduced by putting those energy conservation measures in place. So I just went through 5 different examples, 5 different case studies. The report that we're working on finishing up right now actually has the detailed information for each of those 5 case studies for each of the 7 climate zones, and then also the statewide impact. So our hope is that people will be able to dive into that for their own region or their own building type that they're looking at to get that specific information. But again, just given the amount of time that we have for today's presentation, we couldn't go through each of the 35 case studies in detail. Some of the major conclusions, though, that came out of the report: the energy conservation and adaptation to climate change can really be something that's complementary. There really, again, careful attention must be paid to use, occupancy, the schedules of the building, etc. And as we showed in the different building types, understanding especially things like the type of loads you're going to see in the building, if you're concerned about overheating, is something that needs to be carefully looked at. Improvements to the envelope can also have either positive or negative impacts to exposure to extreme temperatures. So again, thinking about natural ventilation is really critical for heat wave type events. Certainly for the cold side, about retaining the heat in by having enough insulation. In the wintertime, if we have a power outage, we're not as concerned about that. We're really concerned about things like letting the sun come in and being able to ride that out or hold the temperature in. So it does become a balancing act in our temperate climate. One thing we found as we went through and we're doing a literature review to try to set up this project is that better guidance on how to model passive survivability would help design teams, and certainly having things like future TMY files that tracked with changes in the climate could be part of this process. There's a lot of discussion about what the thresholds should be, how we begin to design for these things. A lot of the data is based, unfortunately, on data from the Marines and from the Navy, primarily young men under 25, and that's certainly not representative of our population, and it's certainly not representative of the most vulnerable populations. So getting that additional research and really giving good guidance to design teams is important. And making sure that we have the data to expedite that process. I think a lot of people have said that would be helpful to have in place. And certainly as we look at things like energy efficiency programs, so for this research we looked at the NYSERDA New Construction Program. These energy efficiency programs may want to think about new protocols for studies and look at how it might incorporate things like health impacts, the thermal extremes, and future weather issues. We've had some really great conversations with NYSERDA about this as part of this research, and we're certainly hoping that other states are going to pay attention and be interested in using some of this, perhaps for how they design their own utility type programs. Some of the future work. So this is the last of 6 webinars that we're doing for NYSERDA and for this research project. But some of the future work that's coming out of our laboratory that's related to this. So a study we're hoping to publish here soon took a look at all of the different resilience strategies that are out on the market right now to understand some of the different areas that they impact and also to understand the different ways that different rating systems are framing the issue of resilience. We're hoping to have that out soon. If you follow and go to our website, we'll be sure to post it as soon as it's published. One of the other things related to this study in particular, and looking at some of the trends and changes in things like cooling degree days over time, in addition to looking at some of the building mechanical systems, which we talked about as part of this webinar, we're also looking at passive strategies, so things like sun shading of windows or high thermal mass in buildings or things like evaporative cooling or natural ventilation cooling to see how those may be actually changing over time. Some of the interesting things we found in this case, this is just an example of different strategies for Syracuse, New York. Heating impacts are decreasing by about 140 hours per decade. We actually found that we had pretty significant, statistically significant results for that. And we're also seeing cooling requirements increasing by 25 hours per decade, also with statistical significance. But on the passive system side, as the climate potentially becomes more temperate, there's more actual opportunity for passive solar. So seeing that increase by 40 hours per decade, again, with good statistical significance, which I think is a beneficial thing as you look at some of these different things we talked about today, making sure that the building is oriented correctly, can take advantage of the sun in the wintertime or shade it out in the summertime. But also that dehumidification requirements are increasing. So in a place like Syracuse, seeing that we have 71 more hours per year from 1986, or 71 hours additionally per decade is kind of troubling and makes us need to think about how we begin to alter the design of our envelopes and also some of our systems. So before we wrap up and turn this over for questions, I do, again, want to thank NYSERDA for supporting this research, and especially Amanda Stevens, who has been a fantastic partner as part of this work and a great project manager to work for, and also Tracy Hall at the New York Upstate chapter of the U.S. Green Building Council for really pushing these webinars out to folks and making sure that they had access to them. I do, again, really want to thank the graduate students. Without them, none of this work actually happens. It's also exciting to have people who are potentially future practitioners in New York State, like Hope, who has been silently standing here next to me, making sure this goes smoothly. But without their work on their hard work for, frankly, low pay, none of this stuff would actually be accomplished. And finally, just before we turn it over for questions, in shameless self-promotion, just want to say, please, take a look at the ap.buffalo.edu/adaptingbuildings. Take a look at some of those reports that we're publishing there. We will be publishing this report on the energy modeling there hopefully soon, probably in early June, as it goes through different review processes. But if you have any questions about stuff that's on that page, please feel free to reach out to me. My personal website is ap.buffalo.edu/Rakovich. So with that said, thank you very much for participating in today's webinar here. And I think we'll turn it and open it up. I will try to unmute everybody. Just if you're not going to be asking questions, might ask that you mute it on your own end. We have one question here that came in. With single-family residences being the majority of the building, is there any agency and group that is reaching out to general contractors of this building type so that they can improve their designs? That's a great question. We actually had a research meeting towards the end of 2018, in October of 2018, where we reached out to a number of different organizations like the International Code Council, but also had some contractors from firms in New York State that are taking progressive approaches at that meeting. One of the things that we identified about that is that the residential market is really something that we still need to dive into and get more people involved in that process. And so I think as part of ongoing research at NYSERDA and ongoing research outreach, we're hoping to link up with the ICC and other organizations to make sure that general contractors, understand some of these issues. And especially since these are, again, externally load-dominated buildings, we want to make sure that they're able to respond, quickly to some of the extreme temperature events. So a question that came in, so the ERISA webpage links to all energy efficiency programs. Will there be anything similar for resiliency programs? I think that's a great question. It's certainly something to think about. The site that I had mentioned before, which is the New York Climate Change Science Clearinghouse. I'll just put the slide back up on the screen if I can figure out how to do that. Maybe I can. So this website, the NewYorkClimateScience.org, actually has, in addition to the data viewer that I mentioned earlier in my presentation, has a lot of documents, reports, articles, and plans. That would be a good place to go first. Also, if you go to NYSERDA's website, NYSERDA has a lot of different information on that site. If you don't find something there, it's certainly something that we can talk about trying to link those things up. I also do believe that the New York State DEC maintains a lot of information about this as it relates to climate smart communities, so it might also be something that you take a look at there. So other questions people might have? So one of the questions that just came in through the Q&A is, were the insulation increases in the case studies, were they to meet current code, or was it the value greater to code? So we really were modeling what was the actual improvements to the building at that time. One of the challenges was going through buildings, in some cases, that had been modeled in 2008 or earlier. And so we were looking at what changes had actually happened in those cases to go above the code at that time. certainly think that there is the opportunity for additional studies looking at changes to code currently or even projected future codes, things like the passive house standards, and that really is where some of this energy modeling type research seems to be going. So hope to potentially be able to share some additional studies that others are doing at some point in the future. But that seems to be the kind of the current approach is catching up and seeing where we are right now. But thank you for that question. Well, if there are no other questions, I just want to thank all of you again for joining us today. Thank NYSERDA for its support and also the U.S. Green Building Council. We've really enjoyed doing these last 6 webinars. If you've stuck through for all 6 of them, we appreciate you being and sticking with us, and hopefully they've gotten a bit smoother as we've gone along. But again, please check out this website, and if you have any questions, feel free to reach out to us. Otherwise, we will stop sharing and go off and have lunch now. So thanks very much.